Hello, this is Professor Watson, and I'm continuing my series on the machine learning class. This is the second class of the semester where we talk about basic classification and regression. This is a pattern that we're establishing in the class that is going to happen again and again, where we're going to spend one class introducing a lot of new conceptual ideas and the immediately following class doing a lot of engineering and skill building. So the first class was heavily directed toward learning the basic vocabulary of machine learning, getting the basic idea of a pipeline and the basic intuition of how a problem works in your mind, and talking about some of the kind of major clusters and course structure that we're going to use for the rest of the semester. This class is just for me to mostly get a sanity check on coding skills and coding background in the class. We are going to do two problems. They're going to be the pre-class work. I'm going to go through both of them right here in a second. And then in the class, we will just continue to work through these two problems. Everybody's going to kind of present their work on it, show the code that they had, show how they solved the problems, and make various arguments about what the data shows. The data is exactly the same data that you should be familiar with from the first class. It is the Moore's law data and the MNIST digits data. And what you're going to do is take that exact same codebook, that exact same start that you had last class, and extend it a little bit in this new pre-class work notebook. To show you some of the basics there, in the first question, I'm asking you to do a regression on Moore's law. Moore's law is the idea that the number of transistors on a chip doubles every 8 months. It's been true for a long time. And it's one of the ways to measure this is this data set that I linked to here, which has a measurement of all of the numbers of transistors on chips over time. There are various benchmarks that get run on these. They may not be running on hardware. They may not be run and so forth. So you have to do a little bit of work to clean the data and figure out, what the correct dates are. Once you've figured that out and you're able to plot the number of transistors versus time, I then would like you to run a linear regression model that fits a line to that data. And you might need to log transform the data because this is an exponential growth period. So if you're going to fit a linear regression to it, you'll want to log the data first to put it in log space. All of that, I've linked a couple of code bases here that could be helpful, including a video that explains a little bit of the mathematics behind it. I don't expect you to really dive super deep into the linear regression model. You don't need to go much beyond what appears in the textbook because we're going to cover all of that in a subsequent class. But I do want you to get exposed to those equations. Now I want you to start thinking about them, start recognizing, being able to recognize them when you see them, and to start thinking about how to implement it in Python code. The major thing you're going to have to do here is just give me a plot of the data showing with your best fit line of your regression, showing the data, the Moore's law data over time, and the line fit to it. The second question that I have for you is an MNIST digits question. MNIST is a series of handwritten digits that are in these low resolution pixel maps. I expect you to be able to pull the data from scikit-learn, plot a few examples, and then use a simple logistic regression classifier. Again, I have some helpful example code to classify pairs of digits. So pick like a 7 and 3 and try to tell them apart with a classifier. Report, ideally you'll get to the part where you're reporting your error rate. I hope that you're able to kind of, if you really want to get fancy, you might give me something like F1, precision recall, metrics like that. That's not really what is necessary here. That would be a mastery score. That'd be kind of going above and beyond. If you have extra time, you can test on a full data set. But this is really just, this is a hard problem and takes a considerable amount of time just to kind of get all of the pieces in place. Once it's all written up, it is not very much code. It's 20 lines tops to do all this stuff. But that first push and understanding everything and putting it all together can take a considerable amount of time. So, and then of course, our standard question 3, hey, create any novel study materials. When you're working through this, what did you use? Share these materials in Slack, share these materials on Notion. You'll get some credit for that here. The thing I want to focus on this class is I want to understand that this will not be your only crack at this problem. This is probably a little too much and a little too hard for all but the very, very the students who have a ton of experience in this area. The point here is to struggle with it and to mess around with it for a while, maybe to fail at it, maybe not to be able to do everything that is asked for in this pre-class work notebook, so that because you will actually get a chance to turn in these problems corrected and repaired after class when we turn in our first codebook assignment. So all of these things, these are great examples of stuff that's going to come up in that first assignment where your final draft is. What I expect you to have for today is the first draft of these different coding problems. Again, we'll review them in class. You'll get tons of feedback. You'll learn from your peers. We'll do a little bit of integration of that knowledge with what we learned in theory in first class. And all of this in these first two classes serves as a sanity check to make sure that you are on the same page as your peers, the same page as me, that you have the requisite skills to really benefit from this class. If anything goes wrong when you're doing this, if it is a matter, it's usually a matter of software installation, of not having, the right conda implementation or something like that. A trivial problem, easy to fix, reach out to me on Slack. We'll work through it. If something is mathematically difficult, or if this is intuitive to you, if you don't have the coding background, again, just reach out to me on Slack. These are all ordinary problems in this area. I intend for this to be a little bit too difficult, a little bit too crunchy to get through. It is a challenge. I really would like you to throw yourself against it and do as well as you can in the limited time that you have, knowing, of course, that you'll get one last run of it to really correct it and make it perfect. I want to see your rough draft today. So I'd really like you to try to finish all these problems, give it your best shot, give me your best rough draft. Don't worry about making it perfect. Worry about making it done, worrying about getting it off the line so that we can all begin to understand what coding background we all have and what a good answer to this question begins to look like. Great. I will see you in class.